Okay, let me start the presentation. Okay, hello students, and welcome to today's Math Happy Hour. Today I'll be going over solving exponential and logarithmic equations. Okay, so topics covered for today: writing logarithmic equations into exponential equations, writing exponential equations into logarithmic equations, solving exponential equations by using the same base rule, solving exponential equations with different bases, and solving logarithmic equations by using logarithmic properties. Before I start, this is something that I covered last week, okay? So the first 2 or 3 slides is a repetition of last week, just to let the students know how important this is, okay? So for example, a recap from last week: definition of logarithms to the base a. If you have y equals to log of base a x, means a to the y equals x. Okay, so write each logarithmic equation into an exponential equation. So we're going to be going from log to exponential, right? So we copied down the formula for the log equation, and then I have to go from logarithmic to exponential. So I have to know what the a is, what the x is, and what the y is, right? So we're going to put them down. So my a, if you notice, is 9. My x is 81, and my y is 2. So it's going to be a to the y equals x. So it's going to be 9 to the second equals 81. That's how you write it. Okay. Now we're going to go the other way. Okay, there it is right there. Now we're going to go the other way. Now we're going to write an exponential equation into a logarithmic equation. Right, so again, I need to know what the a and the x is, right? The a, the y, and the x. So the a is going to be 5. The x is going to be 125. Or the y is going to be 3, and the x will be 125. So then it's going to give us y is 3, so it's going to be 3 equals to log base 5 of 125. Or log base 5, 125 equals 3. So this is how we write from exponential to logarithmic. Okay, now we're going to do graphing. Okay. In order to graph without a calculator, must convert logarithmic equation into an exponential equation. So these are examples of exponential equations. And again, we did cover this last week. Just a little recap. An exponential function has the exponent is a variable, and most of the times it's going to be x. Okay, a is my base, and the exponent is a variable letter, frequently x. Okay, it can be y or it can be any letter, but most of the times is x. There's my exponential equation or function. Okay. Now, example, right? We're going to graph this exponential function. So the points that you use, right, or the x values that we use is -2 to 3 or -2 to 2. Okay, so let's do a little table. My f of x is the same thing as y. So when x is -2, right, so I'm going to plug in -2 where the x is, which will give us 1/4, right? We're applying some of the rules that we learned also last week, some of the exponential rules. So this will give us 1/4. So when x is -2, y is 1/4. When x is -1, right, we evaluate f of -1, which means I'm going to plug in -1 where the x is. This will give us 1/2 to the first power, which will give us 1/2. So when x is -1, y or f of x is 1/2. Now 0. Remember the 0 exponent rule? Anything to a 0 power will always be 1. So 2 to the 0 will give us 1. So when x is 0, my y is 1. Now let's evaluate f of 1, which means it's going to be 2 to the first power, right? Because we plug in the 1 where the x is. So it's going to give us 2. So when x is 1, y is 2. Now when x is 2, y will be 4, right? Because 2 squared will give us 4. So when x is 2, y is 4. And finally, when x is 3, y will be 8, because 2 times 2 times 2, right, is the same thing as 2 to the third power, which is 8. Now we get to graph it. So the exponential function, this is how most of the functions, these type of functions will look. They start low and they go up high. Now, if you notice, negative 2 to the 1/4, right? Let's go to negative 2. It'll be about here, where the arrow is. And then when it's negative 1, right? Negative 1 is going to be 1/2. When it's 0, it's going to be 1. When x is 1, it's going to be 2, right? But this is what you grab by plotting all the points. And let me tell you why we don't use negative 3 or negative 4, because if we use negative 3, right? The I mean, the further that you go down the negative negative x values, right, is going to be getting closer and closer and closer to the x-axis, but it will never reach it. So that's why it's useless to use negative 3, negative 4, negative 5, because eventually it's going to get closer and closer and closer to the x-axis, that at times it's going to be hard to plot. Okay, but like I said, from negative 2 all the way to 3 is good, or from negative 3 all the way to 3 is also good. It depends on the base. Okay, now let's graph logarithmic functions. In order to graph without a calculator, must convert logarithmic equation to an exponential equation. That's why I started at the beginning, right? Converting from logarithmic to exponential. And again, here are the rules. So y equals to log of base a x is a to the y equals x. This is a logarithmic form, and on the right we have exponential form. So example, right? So we have to convert it from logarithmic form to exponential form, right? So this is 2 to the y equals x. Now to graph it, guys, we're not going to plug in the values for x, right? Because it'll be kind of difficult to do that. So we plug them in for y. So we're going to use the same values for y, negative 2 to 3. But now we'll be solving for x. So this is my result, okay? And how do we get this? Because if we plug in the negative 2 for y, we're going to get the same values as what we did for x. I mean, when they were reversed. Remember, when x was negative 2, it was 1/4. So we follow the same procedure as we did on the previous slide. But instead of plugging in the values for x, we plug them in for y, the same values. So anyway, the one in blue is the exponential function, and the one in red is the logarithmic function. These two are called inverse of each other. Okay, and I believe in 1324 they don't really cover inverses, but in 1314 they do. So that's why I'm not even going to go over the inverse topics, because we don't see them in 1324. But that's how you graph exponential functions and logarithmic functions. Okay, now here is the main concept for today, or one of the main concepts. We're going to be solving exponential functions. So before we begin, actually doing some examples, there are certain things that you got to know. Okay, for example, to solve exponential equations without a calculator, you need to know previous topics such as, what are perfect squares? 2 squares are perfect square because 2 squared is equal to 4. 3 squared is 9, 4 squared is 16. So you have to know as many of these as you can, at least know all the way to 10. You have to know perfect cubes, right? For example, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and so forth. At least know all the way to 6. We have to know also perfect fourth roots. Like 2 to the 4th equals 16, right? And the fourth root of 16 will give us 2. So this is what you have to know. Okay, also exponential expressions, right? That was what we covered last time. A is called the base, m is the exponent. And you also have to know the exponent power, right? When you have a power to a power, you multiply the powers. And these rules, I covered them last week on the previous PowerPoint that I did last week. And finally, you have to know how to solve one variable equations and maybe also quadratic equations, but most of the times it's one variable equations, like 2x plus 8 equals 14, right? Okay, now here's the first example of solving exponential equations. This is like the rule. It says, let a be a positive real number with a cannot equal to 1. Okay, now here's a condition. If a to the u equals a to the v, then u must equal to v. In other words, if you have the same base, right? A is called the base. If you have the same bases, then the exponents must equal to each other. Let's do a real simple example here. Example 5. For example, we have 3 to the x equals 3 to the 5th power. So do we have the same basis? Yeah, we do. So then we can apply the rule. So the rule states if you have the same base, we let the exponents equal to each other. So my answer is 5. X equals to 5. I like to start out with a simple example because after this one, they get a little bit more, more challenging, okay? So for example, example 6, do they have the same base? Not the same base. So then let's see if we can get a number with a number 8 with a base being 2, like 2 to what power will give me 8. That's why on the previous slide that I mentioned that you have to know the perfect squares, the perfect cubes. This is the reason why. Okay, anyway, you should know that 8 is equal to 2 cubed. So that I'm gonna replace the 8 with 2 cubed, and then bring down the exponent equals 2 to the 5th power. Now here we're gonna apply the exponential power rule, right? Which means when you have a power to a power, you multiply the powers. Now we got the same base, so now we can apply the rule. The rule states, right, if you have the same base, then we let the exponents equal to each other. And now we do is solve a one variable equation, which is we're solving for x. We divide both sides by 3, so the answer will be x equals to 5 over 3. That's my answer, right? But it's always good to check your work. How do we check our work? Is that right? We go to the original equation. We're going to plug in 5/3 for the x. Okay. Is this true? You can either use a calculator or you can do it without, if possible. So if you plug in 8 to the power of 5 divided by 3, it's going to give you 32. If you put 2 to the 5th power, it will give you 32, right? So we know that 2 to the 5th power is 32. But let's see what 8 to the 5/3 is by using the fractional exponent rule. Right, 8/3, right? So we have to go from 8 to the mn and to the nth root of 8 to the n power. So I know that my index, which is the denominator, in this case the n, right, is 3. So the index is 3. The base is going to be 8. So that's going to be the radicand. And the exponent is going to be 5. So what's the cube root of 8? The answer is 2. 2 to the 5th power will give us 32. This is your answer. Most of the times, the instructors might say on an exam to use to do it without a calculator, but not every time it can be done. Without a calculator. There's times that you have to plug into the calculator because it's really impossible or real hard to get it without using a calculator, which I'm going to show you some examples later on this PowerPoint. But in the meantime, guys, this is how you can check your work, but you can always also use a calculator. Okay, now let's continue. How about this one here? Okay, now here's how you start. Right, they're not the same base. So you start, right? So you start with 9. Let's see if 9 to a power will give me 27. So 9 squared gives me 81, right? Which is way more than 27. That means that you have to find the same base from 9 and 27. Right? Find the common basis between 9 and 27. And now if you know the perfect squares or the perfect cubes, right? We know that 9 equals to 3 to the 2nd power. And 27 equals 3 to the 3rd power. You see, so now I got the common basis. So this is what we're going to do. We're going to replace the 9 with 3 squared. And then we'll be done the exponent. We're going to replace the 27 with 3 cubed. Now on the left side, we're going to apply the exponential power property or power rule. Exponent power rule. When you have an exponent raised to an exponent, you multiply the exponent. This will give us 3 to the 2x equals to 3 to the 3rd power. Now they got the same base, right? Now we can apply the rule, which means when you have the same base, we let the exponents equal to each other. So 2x must equal to 3. We divide both sides by 2, so the answer will be 3 over 2. And again, you can always check your work. Because here I'm checking the work every time, but you don't really have to. Okay, I think it's good to check it if you have time to plug in back into the original. So, okay, so here we go. So x equals to 3 over 2, right? So we plug it into the x, and we use a calculator, it's going to give us 27. So we know this is true. So I know that's a solution. You see, they get a little bit more challenging in every example. So on this one, again, we have to find the common base, right? Do they have the same base? No, they don't. So then we say, does 4 squared gives me 32? Right? No, it doesn't. Give me 16. So let's try 4 cubed. Give me 64, right? So that means that is way more than 32. So that means we have to find the common base between 4 and 32. We know that 4 is equal to 2 squared, and 32 is equal to 2 to the 5th power. You see, now we have the common base. So I'm going to replace 4 with 2 squared. We bring down the exponent, x minus 1, equals 32, the same thing as 2 to the 5th power. And again, we're going to apply the exponent power rule. So it's going to give us 2 to the 2 parentheses x minus 1 equals to 2 to the 5th power. Now we have the same common base, right? So now we can apply the rule. So we're going to have 2 parentheses x minus 1 equals to 5. Right? Now we distribute. That will give us 2x minus 2 equals 5. Now we add 2 to both sides. So 2x equals to 7. We divide by 2. So x equals to 7 over 2. And again, you can always check your solution. Okay, I'm going to plug it in there. So 7 halves minus 1 will give us 5 over 2. Now this one, again, you can plug it, you can use the go to the go from exponential to a radical form, right? Or you can just plug it in the calculator. So this will give us 32. So I know this is a solution. If you guys have any questions as I'm doing this presentation, please put it in the chat, and then that way the moderator can let me know, right? Because I cannot see the chat because I'm sharing my screen. Okay, so please don't hesitate to ask any questions if you're confused or you need any clarification. Now, to solve logarithmic and exponential equations, need to know previous properties such as, these are properties that you should know. Okay. This is called the product property. This is called the quotient property. This is called the power property. Product, quotient, and power property. Also with the ln, right? This is with a log. This is the natural log. Same thing, right? When you're multiplying, you're going to expand them, and you're going to be addition. When it's the quotient, right, like division, you're going to expand them, and it's going to be subtraction. On the power rule, if you notice, the exponent goes to the front. See? Okay, now, recall example 7, right? 9 to the x equals 27. Well, I'm going to show you another way to get the answer. And this one will apply anytime. So if some of you guys, if some students struggle with finding the same base, there's always an alternative. Okay, and with this one, you can never go wrong. Okay, let me show you what I'm talking about. So x was 3 halves, right? Remember this was the answer from last time. Solve by using the power property of natural log. So you're going to use the natural log. Remember, you want to bring the exponent down, right? Because you're solving for x, so you want to bring it down. So we're going to use the power property rule. So we're going to take the ln of both sides. Right, so I'm going to take the ln of 9x and the ln of 27. Now, by rule, right, by the property, the power property, the exponent goes to the front. So the x goes to the front. Okay. Now, hey guys, please do not make the mistake. The ln of 9 is a number. It's not separate. It's a number. Okay, so here we're going to divide both sides by the ln of 9. Now you can put that in the calculator. The ln of 27 divided by But the ln of 9 is going to give us 3 over 2. 1.5 or 3 over 2. See, this will always work. So you have an option of finding the same base or by taking the ln of both sides. Okay, now this is what I mentioned earlier, very important. The ln of a number is an actual value, cannot separate them. I've seen a lot of students, they just divide by the ln. If you do that, you end up in the previous step, right? But anyway, that's a no-no, you cannot do that. Okay, it's an actual number. Okay, now here's a rule, right? If you have, this is the power rule that I explained to you in the previous slide. If you have the ln of u to the r goes to the front, you see? And then you don't have no more exponent. So on this one, for example, on this one, if you want to solve it with the same base, there's no way you can get the same base with these two. So at times, it's not possible to find the same base. So that's why we have an alternative to taking the ln of both sides. So in this case, we're going to take the ln of both sides to bring down the exponent. See, I put here not the same base and cannot get them with the same base. You bring down the exponent by taking the ln of both sides. ln. Now by rule, the exponent goes to the front. We divide both sides by the ln of 5. Right, we use the calculator. And this is my result. I put those wiggly lines means approximately. Because in this case, at times, it's going to be like a decimal that never ends. It's called, I believe it's called irrational number. It never ends, right? So that's why you have to round off to like 3 or 4 places, depending on your homework, on the Pearson, or on the instructions of the instructor. They might say round off to 3 places or 4 places, whatever it is. But in this case, we just round off to 4 places. So the answer is approximately 1.2920. And again, you can check your work. But here, guys, you're never going to get the exact answer because we rounded off. You're going to get something real close to the value to 8 here. So we're going to plug in 1.2920 for the x's, right? And then put in the calculator. You see, it will always round off to the value here on the right. It gives us 7.9996, which eventually is the same thing as 8. Okay. Now here's another rule. Okay, if you have log a base day u equals to log a base day v, then u must equal to v. If you have the logs with the same base, then then whichever here for u must equal to whatever there for v. Okay, let's do that example. Example 10. Remember, guys, also last week when we did logs, if you notice, there's no base there. So if there's no base, we know, or we should know that it's base 10. If there's no base, it's base 10. So here, guys, right, log a base 10x equals to log a base 10, parentheses 3x minus 6, close parentheses, right? So they have the same logs in the same base. So by rule, x must equal to 3x minus 6. We subtract 3x from both sides. So it's going to give us negative 2x equals to negative 2. We divide both sides by negative 2, so the answer is 3. Okay, one thing that I must tell you guys, I believe I'm going to mention that later on, but the logs or the ln's cannot be negative. If you have a calculator right now with you, a calculator, just put the log of negative 2 or negative 1, whatever it is, but a negative integer. It's going to say error or undefined, which means there's no negative numbers on logs or natural logs. Also, if you want, plug in 0. Just put log of 0. It's also going to give you error or undefined, which means that the logs, that domain, has to be more than 0. Okay, that's what it's saying about. So if your answer is negative or 0, it means there's no solution for that. That's what I'm trying to tell you. And again, here, guys, right, we can always check our work. So we're going to plug in 3 for the x. So we know that 3 times 3 is 9. right? So log of 3 equals to log of 3, right? So we know it's the correct answer. Okay, now, again, this is using the same property as before. Okay, now on this one, example 11, we know it's base 10, right? Because there's no base. So these are all base 10. But now, hey guys, in order to apply the rule, right, it has to be a single log on both sides. For example, on the right side, you have 2, so this cannot be like this. So you have to put them as a single log. That's where the properties come in. You see, to apply the rule, a single log must be on both sides. Use the product property on the right side. Remember, if it's plus, right? If it's plus, you're going to put a single log, and you're going to multiply the x minus 2 times x plus 3. See? Now, since you have the same log on both sides, the base, right, on the log, you can apply the rule. Now here we have to distribute. Or use the FOIL method. I'm sorry, it wasn't distributed, it was a FOIL method. So x times x will give you x squared. X times positive 3 will give you 3x. Negative 2 times x will give us negative 2x. And negative 2 times 3 will give us negative 6. The 3x minus 2x can be combined. So this will give us x plus 3 equals to x squared plus x minus 6. Now, since we have a square, right, like a quadratic, we have to send all these to where the x squared is. So we're going to subtract x and subtract 3 to both sides. On the left side, it's going to give us 0. Then here it's going to give us x squared minus 9. Now we have to factor. And again, I believe we didn't do a factoring in PowerPoint this week. This semester. But if you guys want, send me an email at the end, and I'll send you the PowerPoint for the factoring part. But x squared minus 9 is factors in two binomials, the x minus 3 and x plus 3. So now you let both equal to 0. Right, so x minus 3 must equal to 0, or x plus 3 must equal to 0. On the left side, we get x equals to 3, or x equals to negative 3. Now here is what I would tell you guys. We can check our answers, right? But remember that I told you guys that the logs cannot be negative? Well, let's see if we get a negative log here. Let's first try the negative. We're going to put negative 3 there for the x, right, for every x. If you notice, not defined because negative 3 plus 3 will give us 0. Log base 10, 0 is not defined. Same thing over here on this side. So if you find one that's not defined, then there's no solution for that one. Not a solution. Let's plug in the 3. So I'm going to plug in the 3 there, and there, and there. So here we get log of 6, log base 10, 6, equals to log of base 10, 1 plus log of base 10, 6. Now, we're going to simplify. Log, if you put log of 1, right, and your calculator is going to give you 0. That means that log of base 10, 6 equals to log of base 10, 6, so I know the answer is correct. Okay, let's do another one here. Again, we're applying the same rule. Now, we have the same thing, but instead of multiplication, here we can have right, it's a minus, so that means it's going to be division by using the quotient property. Right now they have the same base, so now we let x equals to x plus 3 by applying the rule. X plus 3 over x minus 1. Now here we can multiply both sides by, or we can cross multiply or multiply both sides by x minus 1. If we multiply both sides by x minus 1, right, it's going to cancel here on the right side, and we have x times x minus 1. Or you can cross multiply also. So now we have to distribute. X times x is x squared, right? And x times negative 1 will give us negative x. So now we have to set the equation to 0. So we're going to subtract negative x and negative 3 to both sides. That way it gives us a 0 on the right side. But on the left side, we have x squared minus 2x minus 3 equals 0. Now we have to factor. Okay, now for the students that are here in the audience, this Sunday during Sunday numbers, I will be showing students how to factor. Okay, so please show up at 9 if you want to learn how to factor. I guarantee that in 1 hour you should have a better understanding of factoring. Okay, but this one factors to x minus 3 and x plus 1. Okay, so then we let both equal to 0. So x minus 3 equals 0 or x plus 1 equals 0. So we here on the left side we get x equals to 3 and x equals to negative 1. So now let's check our results. Okay, when x is negative 1, let's see what happens, right? Right away we know it's not going to be defined because log of a negative number, right, is not defined. It's not defined. So no solution for that one. That's not a solution. Now let's plug in 3. we plug in 3 for every x. So we get log of 3 equals to log of 6 minus 2, right? Here you can actually put in the calculator, guys. Or this is the answer for both. Or you can do it without the calculator. For example, on the right side, we have log of 6, log of base 10 6 minus log of base 10 2, right? Here we can condense it because when you have the same base, right, by using one of the log properties, I mean, as a matter of fact, it's going to be the quotient, the quotient property. When you have the logs with the same base and you're subtracting, you can put them at a single log and you'll be dividing. See? So we know that log of 3 equals to log of 3. So I know this one's the solution. The solution is 3. Okay, now there's another rule here, okay, that we're going to be applying. This is a different rule from before, so let's read it. If A and U, right, A and U are positive real numbers, where they cannot equal to 1, then A to the power of log base A to the U equals U. In other words, when you want to cancel the log, right, raise it to the base, and that will cancel. So you bring down the whatever there in the place of the U. So U equals to U. Example, right? So what's my base? My base is 3, correct? So we're gonna let both equations here, or both terms on the right and the left, is going to become my exponent, right? I put here, let the expression on both sides of the equal sign be the exponent, and the base of the logarithm be your base. So we're going to put a big 3 there and a big 3 there, right? These are my bases. Now we apply the rule. So this rule is going to be applied on the left side only, right? When you have base 3 to the power of log of base 3 to the 6x minus 2, the 6x minus 2 will just bring it down. Right? So 6x minus 2 equals to 3 squared. So we're going to get 6x minus 2 equals to 9. So since we here, the x is to the first power, right? So we're going to solve for x by sending the 2 to the right side by adding 2. Then we divide both sides by 6. So x equals to 11 over 6. Now, again, we can check our work. Okay, so let's put 11 over 6 where the x is, right? Then we multiply 6 times 11 over 6. It's going to give us 11. 11 minus 2 is going to give us 9. And now here, guys, we can actually put in the calculator, right? Or you can do this, right? Isn't 9 the same thing as 3 squared? And the 2 goes to the front, and log of base 3 of 3 is equal to 1. In other words, you can plug this in the calculator. How do you plug it in? Also, there's also a rule called the change of base rule. Okay? Because in the calculator, this cannot be put in the calculator how it is because it's not a base 10. So what you do, guys, by applying the change of base, you're going to put log of 9 divided by log of 3. That's how we get the 2. Okay. Hey, guys, that's it for today's PowerPoint. It was a little bit shorter than last week's because I want to make sure that I don't go over and I have time to actually have the students ask for questions. I'm kind of apologize that I went kind of fast, but I wanted to make sure that I did finish within time, but I did finish like 10 minutes early. I'm sorry about that. I should have gone slower. Does anybody have any questions?
I have a question.
Yes, Ms. Villalobos.
Could you go to the slide where you're talking about the properties that we need to know?
Okay.
Let me see.
Okay, let me go back, Mika, and share my screen. Okay, so the property. Okay, let me go back real quick. Okay.
Okay, thank you.
You're welcome. Also, if you want, you can send me your email and I'll send you the properties. I'll send you a handout, okay? But still, let me go back over there and see which one you're talking about. Okay, since I cannot see your, let me go back and look for it. Oh, it's here. Please let me know which one was right. Okay, so let me do this. Let me click it here. Let me know, Ms. Villalobos, let me know when to stop.
Okay, keep going. Right there, please.
Okay, Mija, these you have to know these. These are like perfect squares mean like what the square root of 4 is 2, or 2 squared is equal to 4, 3 squared is equal to 9. So please try to know all these right here. And the more that you know, the better you'll be off. And also these are perfect cubes because 2 cubed is equal to 8. 3 cubed is equal to 27 and so forth. So at least know up to 6. And these are the fourth rules. So these are rules that you gotta know before you actually begin solving exponential equations without a calculator. And then, are you okay with that, Ms. Villalobos?
Yes, I'm okay. Thank you for showing me.
Yeah, and also these are the rules that you'll be applying, and all these rules are in your textbook, but or also on your Pearson on the ebook. You can find those there. If you want a copy of this PowerPoint, Ms. Villalobos, send me an email. Okay, I'll put the email in the chat, and I'll be more than happy to share what I have with any one of you guys that's interested. Okay. Does anybody else have a question that I can answer for you right now? Okay, well, I guess that's it then. Hey, guys, but thank you again for
No,
everything, guys.
thank you.
Thank you,
Yes.
Mr. Isati, for this wonderful presentation. If you would like to download a copy of the presentation, you can go to the top right-hand corner of the box and it will let you download. But I mean, the presentation is gone, but you could do that. We do want to remind you about all our recorded sessions, which are available on YouTube on the Tejano Virtual Events playlist. This session will also be available on the playlist later today. Also, linked is a short survey in the chat. We have a short survey. Please help us improve our Tejano virtual event sessions, and if you could take a few minutes just to fill out that survey. Before you all leave, I want to share the Tejano virtual events flyer with the sessions that we will have next week. So for 1 p.m. today, we're going to be having mental health anxiety by the EPCC Mental Health Committee. We will be back with Happy Math Hour next week at 11 a.m., where in Math 1314, we're going to be covering synthetic division and complex numbers. And for 1324, we'll be covering simple and compound interest annuities. Our 1 p.m. session next week will be on body composition by Jeremy Perales. Thank you all for coming in today, and we hope that you all have a lovely weekend. If you have any questions, please use the chat box or use your mic. We hope to see you. We hope to see everybody again for the Happy Math Hour. Thank you for coming.